Okay, so let me share my screen. 1 minute, please.
Okay.
Would you see my screen, please?
Yes, doctor.
Okay, so first of all, I would like to thank the organizers of this meeting for the invitation to deliver this talk. And second, I wish to welcome all of you online in my presentation. Today, I'm going to talk about the hydrothermal or hydrothermal assisted growth of nanoparticles. So this is a process sometimes called, let me show you my agenda, sometimes called coarsening. So I'm going to talk about coarsening today. And I wish to cover all these topics. The first is how universal coarsening is. Actually, it is too much. And how coarsening depends on size. And also there is a critical size. And how is the size, how the size depends on time, which is not a new problem in the literature, and how the coarsening depends on temperature. And regarding temperature, how diverse coarsening is. So this is my agenda for today. And if you look at the literature, coarsening is really a very universal process, natural process, actually. So on the left-hand side of my slide, you can see Syria gadolinium-doped Syria nanoparticles that were deposited on crystalline substrate. And then this material is in contact with a water-based solution. And we can see how the size of the nanoparticles, how they grow as a function of time. For instance, the pictures here are a scanning microscopy, and then you can find not only the diameter of the nanoparticles as a function of time. You can see they grow, starting with a 0 minute on the left and upper hand side of this corner of this picture. And then it goes as a function of time, growing, visibly growing. And also it grows as a function of temperature. So these two parameters are very important for the coarsening. In other words, coarsening is the evolution of the material size, micro or nanoscale materials. And at the same time, on the right-hand side, you can see a picture of the desert. So in Arizona, and then you can see how the scenario is the granulation or the granular picture of this material, how they evolve as a function of position, and also it means as a function of time. So coarsening then is a very wide process in nature. This is the first interesting point. Okay, let me go one more step in detail about coarsening, which has two important critical parameters. One is the size, a critical size, I call here a D star, and also a critical temperature I call T star. Okay, if you are above a critical temperature, which depends on the material itself, and it depends on the medium which is in contact with this nanomaterial, for instance, or micromaterial. So if you are below a critical size, and then things can happen that the mass current, so here is the current of mass going into a material, and then the current goes going out. So if there is imbalance in this in current and out current in such a way that the Jn is smaller than J out, which means it is entering less material than it is leaving the material. And then the particle just reduces the size. So this is one scenario. And then let's say we start last day with a colloidal suspension of this, let's say, nanoparticle. And then a few days later, you have a clear solution, which means your nanoparticle, I'm going to talk in nanoparticle, in nanosize scale, your nanoparticle is completely dissolved in solution. On the other hand, on the right-hand side, you see the reversal scenario. So is the in current mass in current is higher than the out mass current. And if the material is, the mean size of the nanomaterial is higher than the critical size of that particular material, so the particle size just grow up. And then you end up with a suspension holding bigger nanoparticles at the end. Of course, all this process in terms of diameter, below the critical or above the critical diameter, it takes place at one particular temperature, above a particular critical temperature. So what we see in practice, in nature, that the size of the nanomaterial, it depends on time, but also depends on the temperature. And of course, it depends on pH in case of you have a water-based solution in contact of the nanomaterial. And also it depends on the ionic strength. So how it depends on time. This process was solved at early 60s, actually 1961, when two papers were published. How it depends on temperature, it is still open question. And my point in this talk today is to address some comments about how it depends on the temperature. Okay, so how was modeling the coarsening as a function of time? Here is another experimental data. So you see the typical size of the nanomaterial growing as a function of time. And then as you increase the temperature, the curves go diversing in a different way. So we have a set of increasing temperature from 10C up to 50C. And how the size depends on these two parameters. So the size depends on time, and the size scales with time as T exponent 1 over N. So, of course, if you expand this expression, you see that in a very short time, the size dependence with time is actually a linear term here. This is a very important point when I'm going to talk about the temperature dependence on size. So these two papers were the papers that appeared early in the 1961. The first term was published by a famous Russian physicist, Lifshitz. And here, according to the Lifshitz model, N is equal to 2. It means time depends, the size depends on time, exponent 1.5, which is a square root. But also at the same time, a German physicist, Wagner, also published a paper showing that in certain conditions, so n could be equals to 3, which means the size depends on time, as time exponent 1/2 or exponent 1/3. So if you look at these curves here, obviously they go very near to this behavior. Okay. But now how the coarsening depends on temperature. I'm going to show you a set of data which are very different from one another. So you can see in this paper from 2012 that the size of nanoparticles goes strongly superlinear as a function of temperature. This is the coarsening temperature. Okay, so we have a superlinear behavior in this particular case. All these materials are nanomaterials in contact with aqueous-based solution. So another superlinear result was published by Aja et al. In 2008. So of course, the square dots are experimental data, and the red solid line, I'm going to explain. This is a fitting according to the model I'm going to discuss later on in this talk. So it's slightly superlinear. So this is a paper published in 2010. It shows a slight superlinear behavior. And then 2012, we have this data, quasi-linear behavior. So the size versus the coarsening temperature. Particular, this data is really linear data. So published in 2011. And again, another paper showing the linear behavior. And this is mine, straight linear, very fine linear data. And then starts to be sublinear. So we can find data in the literature that the temperature dependence on the size, on the typical size, is sublinear, and strong sublinear data. And finally, a very interesting data which decays as a function of temperature. So you can see how diverse the coarsening process is as a function of the temperature. So when we try to analyze this information, we can see that there are two different trends regarding the temperature influence. One is the thermal-dominated coarsening, and the other one is what we call diffusion-dominated coarsening. So let's see in more detail how this happened. So here I represent on the left-hand side a typical nanoparticle, and it is in contact with the colloidal suspension, aqueous colloidal suspension. And then certainly you have a very small fraction of this nanomaterial in suspension. And then we can distinguish at least three important species here. The ASP is the added species in the particle. So that is the species which is really close to the nanoparticle surface. And then we can also spot the ASS, which is the added species in suspension. What is the difference between ASS and ASP is that ASS is exactly outside the hydrodynamic layer. To cross the hydrodynamic layer, to come from ASS to ASP, you have to cross an energy barrier. We call that it is the energy barrier. So to go from the added species A to the particle surface P, But then finally, we have another important added species, which is SS, is the species in suspension. So these are the three important details or species we can spot in this process. And if you see the data I showed you before from our own experiments, we can see the perfect linear behavior where actually how do we understand this process? So the size growing with the temperature. Actually, we have a species in the surface which is going out of the smaller nanoparticles, and then the added species going into the bigger nanoparticles. So this process evolves like this. This is the picture we can build. Okay? So in terms of calculation, I'm going to, of course, just summarize the calculation here. And then we can understand how the added species in suspension go to the nanoparticle surface and become the added species in the particle. So there is an energy barrier, of course. And then we can calculate the concentration of all these species as a function of position. And then on the right-hand side, you can see the typical energy. The important one is the energy barrier to cross the added species in suspension to the added species in the particle. So you can, of course, perform some classical calculation using classical distribution like the Boltzmann distribution. And then you can see that the size scales with temperature and time. So here is how it scaled in terms of the energy barrier and the temperature. So here is, of course, the thermal dominated term, which is typically the Boltzmann statistics term, and this is the diffusion dominated term. Okay, T is time, and T is the short time approximation, as I mentioned before. So the typical size or the size dependence of time and temperature can be looked at as this expression, actually. So one important point is the exponent alpha, which is the diffusion dominated term. It runs between 1 and 2. Okay, so all the curves I showed you before, let me get back there, all these solid red lines, they are fitting according to this proposed expression for the coarsening. So the temperature dependence of coarsening. Okay, here is a table that I can summarize and make some comments about the all the fittings. So we have, I collected actually three linear data. So the linear or roughly linear is the data from Cabouille et al. We found alpha nearly close to 1 and the energy vary about 17.71. In my own paper, so we found the time dependence alpha is nearly 1, and the energy barrier is 127. Okay, so the third data, it fits the alpha exponent, which is the diffusion dominated process, is 125, and the energy in this range. Okay, so if you look at this data, all linear, you can see that the alpha exponent, which is the diffusion term, is on the range between 1 and 1.5. And the energy barrier is in this range from 100 to 600. Okay. So if you go to superlinear, like these three data here, we can understand that alpha is over 1.5, actually, or nearly 1.5. So all these three data show in the feeding process, alpha nearly above 1.5 and of course below 2. And the energy barrier goes a little bit higher than in the linear case, goes up to 1000. And if you go to sublinear, so the scenario is alpha is nearly 1, like the linear case, some cases. However, the energy is higher than 1000. And finally, the decay curve that I show you, the last one, let me go back there. This is the decay curve, completely different from the behavior showed before. So if you go this, you find also alpha is linearly, is very close to 1. However, the energy is high and negative, which means the expression here goes positive in this expression. That is the dominated term that leads the experimental data from the case scenario like this one. So finally, there is a proposal for the coarsening process as a function of time and also as a function of temperature. The temperature dependence is a where the typical size of the nanomaterial or micromaterial scales with a thermal-dominated process, one expression like this, which comes from the Boltzmann statistics, and a term which is a diffusion-dominated term. And this looks like this approach can explain quite well the data we can find in the literature. Okay, I wish to thank all of you. And again, thanks to the organizers of this meeting. And thanks all of you online attending my presentation. Thank you so much. I'm ready to take the questions if you will. And also here is my email address. So those who want to be in contact with me, please, you can take this address. Thank you, Mr. Chair.
Thank you, Professor, for your presentation. Any questions from the group?
Yes, I raise my hand. My name is Angelos Evstathiou.
Yes, please.
Yes. Okay, very nice presentation indeed. I'm wondering about the formation of secondary particles, and those are what we see when we finish the synthesis process, and we end up with a powder. Okay, so these secondary particles come from the aggregation of these primary particles that we measure by XRD. So how this model can predict size of secondary particles, I would say.
Okay, very good question. I really appreciate the question. Let me get back here and see if I understood your question. Okay, so I think this picture can help to make some comments about your question. First of all, in the model I'm proposing here and presenting here today, which is assume that we started with a colloidal suspension. So this is the idea of the model. So if you start with a colloidal suspension, let's say a true colloidal suspension, you might guess that the level of aggregation in the colloid, if that is a stable colloidal, so the level of aggregation is small actually. So particles are separated. It's not like a powder. And this process, the coarsening process, requires that the material you were talking about is in contact with the liquid phase. So it's not the powder itself. So first, so this is the scenario. You start with a colloidal suspension with a small level of aggregation. And then, so there are two ways. Those who have been working on the bench and making synthesis of nanomaterials, let's say in liquid phase, they know about this. So sometimes you do your synthesis one day and then wait for the next day. Next day you come to the bench again and you see a clear solution there, which means this was the process that took place. On the other hand, there is the reverse process where the balance between J in and J out is in such a way that what I call the add species in the particle just leave the smallest particles and go to the bigger ones. So, and then you see, many times you see a precipitation. And this precipitation could be, for instance, due to the coarsening process just increasing the size of the mean size of the nanoparticles. So this process takes place is, we think about this process when the nanoparticles are in contact with the liquid medium. And in particular, to be able to derive the equation I showed you later on, which is this equation, we need to assume that we have let's say, a stable colloidal suspension where all this process can take place. So you can identify at least these three species to handle all the calculation, and also the energy barrier, in particular the energy barrier that the added species in suspension goes to the added species in the particle, and that needs to cross, of course, the hydrodynamic layer around the nanoparticle. So all the elements on this model, it requires that the nanoparticles are in suspension. So I hope I could address your question.
Yes, indeed, but can I further expand a little bit my question? Okay, you clarified that we're talking about colloidal suspension. The question now is this ASS species, for example, and the ASP species, are they in solution from the beginning? So you start with a colloidal suspension, having also at the molecular level, let's say, other type of species in solution.
Okay. Yeah, good point. Let me take, for instance, a very standard colloidal suspension, let's say magnetite colloidal suspensions, for instance. Okay, what would be the add species in this particular case? Add species could be, for instance, iron 3 or iron 4 in suspension, and we know that iron 3 and iron 4 in suspension, aqueous solution, they are complex. Okay, so they are complex by water molecules. Those are the added species in this particular case. And how do they are in solution in the colloidal suspension? Okay, it should be the leftover iron 3 and iron 2 in suspension as a coordinated by water molecules, or so